Hey everyone, my name is Samantha Chan. I'm a product marketing manager here at Ouster, and welcome to today's webinar, Zero to SLAM in 30 minutes or even less. We're so excited to have our partner Kudan join us today for this interactive workshop. Kudan is a leading provider of artificial perception software, and specifically SLAM, for a variety of industries, including automotive, robotics, and mapping. We do have a packed agenda for you all today, so with that, let's get started.
Great, thank you, Sam. So my name is Juan, and I'm the CEO of Kudan USA. My partners in crime today are Yoshi from Kudan and Krishtof from Ouster.
Yeah, hi, I'm Krishtof Korda, and I'm a field application engineer here at Ouster, and I'll be doing the live walkthrough here.
Great. So we have an exciting agenda for today. So as you may know, Ouster and Kudan have recently launched an evaluation program to help our customers quickly assess whether SLAM is the right solution, right for their solution or product. So in a nutshell, simultaneous localization or mapping, or SLAM as in short, is a computer vision-based method that allows you to use sensor data, traditionally from cameras, but more importantly for today, LiDAR sensors to create a machine understandable model of the world in the form of a point cloud, and at the same time, precisely keep track of the location and pose of the device in that space. So you can think of SLAM as two independent processes running at the same time. So one is basically creating a map, and the other one is trying to understand where the device is on that map. And so these maps are created by looking at what the LiDAR sensor sees, and we extract the unique and stable features from the surrounding areas. And then using those points, we create a 3D map of the world using these points, and they're in a point cloud. But because of the nature of the LiDAR sensors, we know precisely where each and every point is and how far they are from the sensor. And especially with Ouster's high-resolution digital LiDAR, you get additional data such as calibrated reflectivity and near-infrared that improves the accuracy of object detection and robustness of localization algorithms. At the same time, the algorithm, while it's creating the map, it's also matching the feature point that it detects against that point cloud, and it compares to assess its location, as well as the pose within that point cloud map. Traditionally, so getting SLAM working on a system was a long and tedious task, and especially challenging when sometimes you're not even sure if SLAM will work for your use case. And even if you were to use an open source SLAM algorithm, getting it up and running and properly configured, it easily took weeks. And then moving on from that and optimizing the algorithm to be commercial ready, that's typically an ongoing multi-year process where you're going to have to continually invest resources to keep it up and current. And also, while you might end up with a highly specialized custom in-house SLAM solution, but through this evaluation, we wanted to help you, take some of that guesswork away up front to determine whether SLAM is the right solution for your business. So hopefully by the end of the evaluation, you'll know that you're on the right path with SLAM, and you'll choose both Ouster LiDAR sensors and Kudan's SLAM algorithm to be part of your solution. So to that end, let's get started. So this is, again, Zero to SLAM in 30 minutes.
Cool. So you'll need a few things when we do this walkthrough today. You'll need the evaluation software, and all of this is going to be available in the handout that Sam mentioned earlier. So that's it's in the GoToWebinar control panel down towards the bottom. There's a handout section. If you click there, there's all the links that you'll need. We also have in the handout the sample data in terms of a PCAP file, and we also have the bag file itself. So if you need to download that, those are all available for you. You also need an Ubuntu machine running either 1804 or 2004. If you're running 1804, you'll be using everything that says ROS Melodic. If you're using 2004, you'll be using ROS Noetic. And you'll see that's what I'm going to be using today. is ROS Noetic on 2004. We're also going to assume that you're starting from scratch, so you'll see we're going to go through basically getting ROS installed and everything. If you don't have an Ubuntu machine for some reason, you can use either a virtual machine like VirtualBox or something like Docker, and we've provided here some Docker pull commands that would allow you to basically build either an Ubuntu in Melodic with ROS or Noetic. So make sure, again, check out the handouts. All the links are there. And now I think I'm going to switch over and we'll start sharing the screen. Okay, so let's go ahead and install ROS. Again, we're assuming you're starting completely from scratch. So you don't even have ROS installed, so we're going to quickly show you how to do that. I'm going to bring up some commands right here, and these commands are available directly from the ROS installation website for the distribution of your choice. Basically, if you're using 1804, you're going to be using ROS Melodic, and if you're using 2004, you're going to be using ROS Noetic. In my case, I'm going to be using ROS Noetic, and here are all the commands that have to be done to essentially install ROS. I've actually already pre-installed ROS on this machine just because it does take quite a bit of time. So to save you that time here in the webinar, that's pre-installed, but I'll still run the command so you can kind of see a little bit of what the process looks like, although everything's going to be saying it's already done or already exists. But then we'll install that and then we'll move on to the next step. So here we go. So it's basically going to add the package list. It's going to find all the packages that it needs from the repo. It's going to install all of them. Any dependencies are going to be searched for and installed as well. If you've already pre-installed it, it will throw an error that you already have a distribution list, but that's totally fine. So once this wraps up, then it looks like we are good. Just to verify, we can run a command called, what is it here? Let me find it. ROS version -d. Great. Now that shows us that we are indeed done with the installation of ROS, and our ROS version is ROS Noetic, which is appropriate for me since I am on 20.04. All right, let's clear the screen here and get ready for the next. Okay, now what we're going to do is we're going to actually set up a working directory for all of the things that we're going to be doing in ROS. So we're going to create a main ROS directory, and this is where we're going to store both of the ROS nodes. One ROS nodes for Kudan, and then another ROS node for Ouster. So let's go ahead and do that. Let's actually make a directory called ROS, and I'm doing all this within the Kudan Ouster webinar directory, but you could do this anywhere on your computer as long as you just create a place for it. So let's make that directory. Let's go into that directory. And then inside of here, let's make two new directories, one for Kudan and one for Ouster. And for now, we're going to jump straight into the Ouster directory. Great. So next thing we need to do is we actually have to download the Ouster ROS node. And I'm going to be showing you how to do that really quickly here. So you're going to go to github.com ouster-lidar /ouster_example. You can also find links to this on the Ouster website, so ouster.com/downloads. So I'm already here on the website, and this is all the code that you're going to need for the Ouster ROS node. And to pull that code down, you can do a few different things. If you're familiar with Git, you can obviously do a Git clone. That'll get you up and running through your normal means. For the purpose of here, for people who might not be familiar with Git, we're going to just download the zip file. And the zip file is going to contain all of the code that you see here on the GitHub page. And that's going to be used for the ROS node. So let's go ahead and download that. We're going to actually stick this in the Ouster folder. So let's go ahead and download that. And let's check that it arrived where it was supposed to. So let's list out. Yep, there it is. All right, next thing we got to do is simply unzip this. And that's going to inflate this all out. Let's check. Yep, we have the new folder there, Ouster example master. And just for cleanliness, we'll go ahead and remove the zip file, which is always a good habit. And we'll confirm that we did that. Great. Yeah. Okay, that's all good to go then. All right, now that we've unzipped and we have everything we need in there, we're going to first double check that we have all of the packages installed that are required for the Ouster example. So to do that, let's first update our package tracker, make sure we have everything up to date and the latest for all the packages we're about to install. And that's good to go. So now I'm going to pull up a command that's going to basically install all the packages that we need. So JSON CPP. Great. So this is, you can do this all in one command or you can do this individually. Basically, we're going to apt install all of these packages here that are all prerequisites for the Ouster ROS node. Now, I've already installed these since I use these all the time, but you'll get to see a little bit of it here. So it'll basically say that we're not installing any new packages because they're already pre-installed. So here we go. Great. No newly installed packages. For you, again, if you don't have these installed, you'll probably see a bunch of new packages that were installed, any dependencies and things like that. So now that we've done that, let's actually change directories into the Ouster example master, and let's see what's inside here. This is basically all the code inside this folder is everything that you see over here. So if we click over to here, this is all this code here, same code that we just cloned here. We did the zip file version versus the cloning. Now let's change directories into Ouster ROS, which is where all the ROS node code lives. And from here, let's do our cmake command to actually prep everything and get it ready for the build process. So we're going to build this in the release type. This is important so that you get full performance out of the ROS node. If you've ever built in debug mode before, you'll know that that puts out a lot more logging and things like this, and that will slow things down. So just always make sure when you're building this, you build it in the release mode. So we're going to go ahead and do the setup now. And again, I've already in the past built this, but I deleted it. So now this is a completely fresh install of Ouster ROS. So this should look very similar to what you'll see in your version. Okay, now that the build preparation is done, we can actually do the full make, which will compile the code. So let's go ahead and do that with the make command. And here we go. It's going through and it's doing the whole build process. This takes a little bit of time. It's not too long. And while we're waiting for this, I can tell you a little bit about what's coming up next. Once this is done, we always have to make sure that we source the setup file. So anytime you have ROS nodes, each time you open a new terminal, you're going to want to make sure that you source this setup.bash or setup.zsh, depending on which shell you're using. Throughout this presentation, you'll see that I'm using ZSH, so I'll be using the setup.zsh files. So once this is done, we can go ahead and get that sourced. And again, anytime you open a new terminal, you're going to run these source commands. We're going to see something similar with the Kudan ROS node, that they'll also have a setup file that needs to be sourced whenever you open a new terminal window. And when it comes to the Kudan node, you'll see there's a -- extend that is appended to the end of the sourcing command, and that basically makes sure that it's going to compile everything, including the Ouster packages. If for some reason you forget to do that -- extend, you may see something that says packages not being found. That's your clue that you forgot potentially to do the -- extend on the KD ROS our KD Lidar ROS node. Cool. So this is done. So let's actually do our source command. So we're going to source, and we're going to get the Ouster version of this. It looks like I don't have it in the history, so I'm just going to go ahead and type it in right here. So it's in the development folder, and it's setup.zsh. Again, if you're using bash, just use the setup.bash, or if you're using some other shell, you can use the setup.sh. So let's do that. Great. So what that does, it sets up the paths in the background for the terminal, so all of the packages and everything can talk to each other, and everything's on the path, so it can be accessed. Cool. All right. So now that that's set up, let's go back a few directories. We're going to go back to the Kudan one, and that will help us to build that node as well. So let's change directories into Kudan. And here you're going to be actually downloading the links that we talked about earlier. You either got them when you registered for the webinar, or I believe we've put it in the chat as well. But basically, click on the link for your distribution of ROS. And in my case, again, we're on Noetic because I'm on 20.04. And I'm going to be downloading this KD Lidar ROS Noetic package. So we can click on it here, and then there's a little download button up here. Direct download. And we'll do something very similar. We'll stick this in the Kudan folder, and then we're going to do the same thing. We're going to go ahead and unzip it. So once we download this, let's confirm it is indeed downloaded. Let's unzip it. Great. That's inflating right now. And check that it worked. Yep, there it is. And again, we'll do our diligence and make sure that we delete the zip file before we move forward. Make sure everything's cleaned up. And there we go. All right, so we have the KD Lidar ROS. It's all unzipped. And here the process is a little bit easier. You can skip straight to sourcing this setup file, again, using that -- extend. So let's search for that -- extend in my history there. And here we go. And if we source this, this will do everything all in one shot. So this is the only thing you have to do. Just remember, every time we open a new terminal, we want to make sure we do the source for the Kudan ROS node and also the Ouster ROS node. So boom, and that's it. Cool. So now we're all done. We've set up ROS. We set up both of the ROS nodes, both for the Ouster and the Kudan. And now it's going to be time to see some SLAM in action. Since you may or may not have an Ouster LiDAR at this point, we will be using a ROS bag to simulate the LiDAR data. You should have received a link to the download to the sample ROS bag we'll be using. However, we'll briefly cover how to run, LiDAR SLAM on an actual sensor in real time here in my room, so that you actually have a view of how that works. Okay, so the basic command to run the ROS node or KD Lidar ROS is pretty much all the same, and then you have some additional flags that you can add for the different options like replay or bag file pass and things like this. So I'm going to pull up an existing command that I've run in the past, and we're going to edit it a little bit based on where everything's located. So let's search for that really quickly. So we're going to look for the word replay because that should get us what we need. Yep. Cool. So what we have here is you have a ROS launch command, and that's pretty standard anytime you're launching a node in ROS, and we're going to be launching the KD Lidar ROS node, and then we're going to be using this launch file to actually launch it. And then we're going to add a few little options here that we need when we're actually playing back from a bag file and trying to do SLAM. So the first thing is the replay is going to be set to true. We're going to do a replay rate of 50% in this case, just to give you guys a little bit more to look at and digest before it's just moved on. We need to give it a bag file path. Recall here that the path needs to be a full path, so an absolute path, not a relative path, so you can't use things like the tilde or the dot or anything like that. Make sure you use the full path from root. In this case, it's my home directory, and then it's in the Kudan Ouster webinar ROS, and I've actually moved this recently, so we're actually going to move this. This is in the bags now file, and we're going to be running the SLAM on a bag file collected in San Francisco on the Embarcadero. And then same thing here. We are going to have to provide the metadata. The metadata is basically the path to the file that Ouster needs to decode the UDP packets that are inside the ROS bag, so that it can actually do the intrinsics, find out where each beam is, the azimuth angles, the elevation angles, and then decode that into an actual point cloud. So this again also has been moved, so let's put this back here. And it's a JSON style file, and that'll give it all the information that's needed to actually run this. And so when we run this command, we should see an RViz window pop up, and in that window we'll see the SLAM being registered with each of the packets that's coming in and being decoded by the metadata. So here we go. Let's give it a shot. All right, so now it is up and open, and let's zoom out a little bit and see what's going on here. So looks like we're getting the live data. Looks like it started out by making a turn, like a U-turn on Embarcadero, and it's starting to register points here. You can see, and I'm going to actually pan this a little bit so we can keep this more in frame for everybody. And you can see how the map is being slowly generated. You can see it's registering and keeping the points, aggregating the points as we go, and building this map. Now this is a sparse map. Basically what that means is it's only keeping points that it thinks are relevant for actually maintaining and building the map. There are options that you'll see later on that we can do that will actually keep everything, basically make a very dense point cloud, and you can adjust your voxel size. The voxel is basically a cubic volume similar to a pixel of how much data you want to keep. Basically, if you have multiple points within a certain voxel size, it'll basically take all of those, condense it into a single point at the center of that voxel. So here looks like during the drive they were at a stoplight here. So let's actually talk through right now a little bit more about the next step here. So the next step we're going to do is we need to actually save this point cloud that's being registered right now into some kind of a file. A pretty common file type for saving a point cloud map is a .ply file. And so that's what we're going to do next. So to do that, we're going to run a ROS service call. And again, for best practice, we're in a new terminal, so let's make sure that we appropriately source the LiDAR or the KD LiDAR ROS node in this new terminal. Remember, that's always a best practice, and not to forget the -- extend so that it makes sure that we're pulling in the Ouster stuff as well. Great, so now we source that. Let's do the ROS service call. And we're going to actually save this in the folder you see here. So the service call is going to be the call to the KD LiDAR ROS PCL save PLY service, and the path is where we're going to save the map to. So we'll save it into the ROS folder. And basically what this will do is this will save the current state of the map wherever it is right now in real time that we're seeing. So if we save it right now,
will only have as much as the map as they see at the current moment. So let's do that right now before this package is, or before this bag file is completed. So let's do that. And success equal to true, and you can see here saving PLY and then the path that was actually saved to. Just in case for some reason you forgot or you mistyped something, it's not what you thought, you can always look right here and see where it saved the points. And let's actually check that. So let's change directories into the ROS folder and let's see what's in there. And look at that, now we have a mymap.ply file. And again, the map is continuing to build over here and being stored in memory, but we saved it at a point previous in time. So that's how this will work with the KD Lidar ROS node. Cool. And actually, we can stop this. Actually, we can leave it running in the background. Hopefully, it won't interfere too much with the performance. But let's actually open this up now and see what this looks like in a program that can view a map. And the program we're going to use is called Cloud Compare. And this is freely available online. There's a viewer and a full-on editor where you can actually edit the point cloud. In this case, we're just going to open up the viewer. It's a little bit simpler, a little bit lighter weight. So we'll wait for that to open. All right, and this has Cloud Compare has a little bit of a trick to it where you can't really do anything by like opening the file normally. You actually have to drag and drop. It's a little quirk, but it is, once you know it and you don't bang your head against the wall trying to figure out how to do it, it'll be very nice. All right, so let's make this full screen. We can add some shading. There's a couple of shaders that come default in here. That'll make it look a little bit nicer. And here we go. This is our map. And now we can rotate this around. We can inspect the map and see, you know, how well did we do. And it looks really, really good. So you can see here, this is the map of the Embarcadero. And again, this is the map up to the point where we hit save. Anything that was mapped after that, we could save into a new and separate file. So here we go. You can see all the nice details of the building, the windows, the trees, and yeah, it's really cool. That's it. That's how you get up and running with getting a point cloud. And as I mentioned before, you know, this is the sparse version of the point cloud by default. So there's only enough information in here to generate and build the map and register the features. If you want to have a more dense point cloud, there's some parameters that we can adjust in a YAML file. And I'm going to go and show you exactly where that YAML file is located in just a second here. So let's close this out and then we'll jump over to where we have that. So the map is still registering in the background. We'll go ahead and kill that right now, just because that's going to eat up some resources right now, and I already pre-built the entire map. Actually, it just finished. Perfect. So it finished cleanly. If we want to, we can actually save this map again, and this will be the full map. So we can use that previous call that we did, and we'll just call this full. And we can save that out, and basically that'll be a slightly bigger map than the previous one that we saw, which will be cool. All right, so that means we can kill this. Great, and then let's clear some things up here. Let's clear this out as well. And let's show you guys how to edit a YAML file. So I have this already opened up in the background here. Great, so this is what the YAML file looks like. The main places that you're going to focus your attention for tuning are basically the under the LiDAR type. You can do change the voxel size, so you can change the voxel size. And again, the voxel size here is in meters. So all these values are in meters. Basically, a voxel size of like closer to 0.1 is good, better for indoors, whereas outdoors, because there's so much data coming through and it's such a large map, you may want to increase the voxel size to something like 0.5 or something like that. We used 0.4 here for what you saw in the demonstration here, so that worked out pretty well. You can also build a dense map like we talked about earlier, and to do that you would just basically turn both of these to true, and that would ensure that you actually get a complete point cloud, not just the registrations that are needed to build and maintain the features of the map itself. So for example, when I did this in my room in practice for this, I initially set it to the default parameters that you see here, and there was almost no detail to the room. I couldn't even recognize items in my room, or barely recognize that it was my room. It was my room. But once I switched it to a smaller voxel size and I increased the density and I set these both to true, then I was able to see everything. I could see my couch. I could see, all the mess that's in my room. Everything was nice and visible once I set it to dense. So that's something that you can play around with once you start using this. And actually, we can actually test this really quick now that I think about it. So let's just set these both to true and save this. And we can go back and rerun this, and then we can save the map after a few seconds here. So let's pull this up. And this goes a lot slower because it's super dense. So let's name this dense. Let's see where we're at so far. All right, let's go ahead and save this out and see what happens. Okay, that was saved. Let's kill this. Let's kill it right through here. Okay, so let's go to Cloud Compare again. Go to the viewer. And let's see the dense point cloud. Let's see if we got any data out of that. Wasn't showing up in RViz, but it is super dense. But oh, here you go. So now you can see it's a lot more dense. There's a lot more points on the ground. There's, we only did a few seconds, and you can see when I zoom in, it looks like it's sparse, but that's just the rendering. And then if I let go, and you can see how many more points were built with the dense version. This is like basically keeping almost every point, except for taking account for the voxel size. So that's a good comparison there for what a dense point cloud would look like if you set that to true. Cool. So let's close this out because that's gonna take up a lot of memory, and let's set these back to false for any future stuff that we do here in a second. Great. So we're going to pause here for a quick second, just in case any of you have been following along in real time. Maybe give you guys a chance to catch up if things are going a little bit too fast, because I know we've practiced this and we were a little bit smoother on it. So just giving you guys a little bit of a break here for a few seconds before we roll into the section. Okay, so Next thing we're going to do is we're going to roll into how to connect a live LiDAR sensor. So if you happen to have an Ouster sensor already in hand and you want to start doing some real-time LiDAR SLAM, we're going to show you how to do that, as well as how to record some live data so that you can actually play it back later on offline and do the SLAM offline. So let's say you're out at a job site and you just want to go and collect the data. You don't want to actually do the saving of the map and doing all that. You just want to collect the data. We'll show you how to do that as well. Okay, so I'm going to turn on my sensor here, and we should start hearing it spin up, and then we can move on to the next section with how to do that. So let's clear this out while we wait for my sensor to boot up. All right, and we're going to use a built-in Linux command called Avahi Browse. And what Avahi Browse is, it's basically a service discovery browser. If you've ever worked with the Bonjour service for like your printer, like how it finds your printer on the network and things like that, that's using what's called multicast DNS. And Avahi Browse is a multicast DNS service browser. And this command here is basically going to browse for the service named _roger._TCP. And that's basically our Ouster sensor. The Ouster sensor always has the service name Roger, as in Roger that, I hear you. And then the flags here, -LRT, that's to look up a service, that's to resolve the service, and then T for timeout, after you found basically a completed list of things that are available on the network. Now, what's really cool about Avahi Browse, it's really good at finding services. Even if the subnet is set incorrectly, you don't have the right IP address, whatever it is, it'll find your sensor for you, and it'll probably tell you what the IP address is that the sensor thinks it's at. So if you've lost your IP address for some reason, you can't find it, this is actually a really good way to find it. So when we look at that, what you see here is we have the IPv4. The plus symbol basically means it's something that it's found, and then the equal symbol is something that it's resolved, meaning it queried and actually got the data out of it, such as the host name, the address, the port that you can reach it on for TCP communications, and then some basic text information like the firmware serial number and the part number. So for our purposes, we're going to use this host name here, and we're going to include the .local portion of it. All right, so next thing we have to do is pull up a very similar ROS launch call that we did previously. However, this time we're going to be using the live version of it, which will have the sensor host name in it. And this should be in the history there. So this is actually the recording version. So let's cancel that one, and let's find the one that is without the recording. We'll do the recording one next. So this is the one for just live SLAM that you can then save your PLY file from. So real quick, going over the command, ROS launch again, we're launching the KD LiDAR ROS node using the launch file. We need to give it some information. We need to tell, okay, what sensor are you actually going to be playing live data from? So the sensor host name is one of the parameters. Remember, we copied that earlier. That was this sensor host name down here. And then the next thing we have to give it is the destination address. So the destination address can be queried very quickly in Linux with IP-ADDR, and this basically queries all of the interfaces that you have on your computer. And you can see here Ethernet 0. Here is the IP address that we're going to be sending the Ouster data to. That'll then be brought into the KD LiDAR ROS node for slamming. So let's go ahead and do that. And again, we'll get another RViz window popping up. And you might have heard it, but it configured the sensor. And now we have our ROS node up and running with RViz. I'll move this more into the center here. And basically, once it starts to register and it sees everything's working, it's starting to update map points. Then I can pick up my sensor. So I'm actually going to pick it up right now. And I'm just going to move it around. And you can see it's starting to generate the trajectory there. And it's starting to scan and actually build the map in the room. And again, like we talked about, this is what I was talking about earlier. The sparse and the larger voxel size doesn't really lend itself well to building a map indoors like this. And so you can see there's not much detail that you can see inside my room, and I think that's a good thing right now. But you guys are more than welcome to play around with this if you have a sensor at home, and you can adjust the voxel size down to maybe like 0.1 and then set the dense map equal to true. Cool. So we've moved the sensor around a little bit, so we've actually done some SLAM here, and you can see what's been captured here. And we can actually save this with the same raw service call. So let's say we want to save this now as my map indoor. So go ahead and do that. And there you go. It's been saved. It's been saved. Verify that it's there. There's that indoor map. Since we've saved it, we can go ahead and kill the ROS node. And let's do the same thing we did before. Let's open up Cloud Compare Viewer. Let's pull in the indoor map. Remember, drag and drop for Cloud Compare Viewer. And here we go. So again, you can see super sparse, right? Because there's not much, information in my room here. It just needs enough to actually build the map. And it's starting to build the map here, and you can see that there's basically walls, ceiling, and that's a little bit of outdoor. So all this out here is things outside my window, and that's what it's stored. If you made this again more dense, you would see actual features in the room, like the couch and again the mess and all that kind of thing. So we left it in sparse mode. All right, let's close that out. Okay, now let's actually take a look at how you can start collecting some ROS bags and actually doing recordings and make a nice collection of ROS bags that you could use potentially for regression testing or comparing some different tweaks and optimizations against identical data. So you've collected the ROS bag, you change the YAML parameters, the voxel size, the density, those types of things, and you can test it over and over again on the same ROS bag. So let's see how you can actually collect one of those ROS bags from the live sensor itself. So let's clean some things up here. All right. So now let's pull the ROS launch command that we were trying to get, that we got last time when we were trying to get a different one. So let's go to the record. So here we go. So ROS launch command, very similar again, launching the node using the launch file. We're using the sensor host name to know which sensor we're going to be collecting the ROS bag from. The destination IP address where the sensor is going to send the data, the LiDAR mode itself, so 1024 by 20, which is 1024 horizontal measurements plus the 20 hertz spin rate. So you get 20 frames per second, 20 full rotations per second. We're going to set record. This is a new parameter. We're going to set record equal to true. And then we're going to give it a bag file path to actually save the bag file. And same as before, we're going to make sure we use full paths, absolute paths from the root, no relative paths like the tilde sign or dot sign or anything like that. And we're going to save it in the top level. And we're just going to name this one bagfile.bag. And another parameter, same as before, the metadata file, so that we know what the LiDAR intrinsics are, so we know how to decode the UDP packets that are coming from the sensor and store them into the bag file. Cool. So this should, again, launch everything as before. You'll get an RViz window, and you'll also immediately, it'll start recording the data into the bag file. Whereas previously we were just doing it live. We were building the SLAM map, but we weren't actually saving the data for the future. So as soon as we killed the RViz, there was no data for us to go back to and rerun this multiple times and do tweaks with the voxel size and things like that. Okay, so I can do the same thing again. I can pick up the sensor, I can spin it around, I can do some things with it to start mapping my room. And we can put it back down. All right, and that's pretty much it. You saw quite a bit of material here. Hopefully, this video will give you a resource that you can come back to and look at, and look at sections of the video and understand how to do everything, in case it didn't all sink in today, which would be hard for it to, because it's a lot of information. So we covered all the basics here. We plan to do some more of these in the future, and Juan is going to talk a little bit more about that. What are some of the follow-on things that we might do, and some details that'll help you guys getting up and running as quickly as possible. So yeah, there you have it. Real-time recorded bag files. You know how to do it all now with the Kudan SLAM and the Ouster sensor. So I'm going to hand it over to Juan right now. Thanks, everybody.
Juan, you might still be muted.
Thank you. Thank you, Krishtof, for the great walkthrough. I know we've covered a lot of material today, but with all of this, you should be able to start working with LiDAR SLAM and experiment with how SLAM could work as part of your solution. So there's basically three common things that we see our partners typically walk through in terms of evaluating SLAM. And so basically, you start out with the map and trajectory accuracy against some ground truth, if you do have ground truth available. And this will test basically how good the point cloud maps are, and how well the tracking is working within the movements in that space. And you can see it both from a relative perspective and absolute standpoint as well. So you can make that assessment whether it fits your environment and operating parameters. The next thing is repeatability. So you see a lot of these autonomous vehicles and robots tasked to do repeated movements and touching waypoints along certain routes. And through this testing, you can basically see how accurately the device returns to a specific position on the map. And especially when you have obstacles within that course, how it can reroute and still hit those waypoints, and see if that works for you. And finally, we look at relocalization. And so relocalization is the ability to, at any arbitrary given point, to know where you are. So in cases where tracking can sometimes get lost, or if you initialize a device in some random position, you test how quickly it can actually figure out where it is on the map and how quickly it can recover. So I think these are three starting points for your evaluation. But let us know. I mean, if there are things that you want to see, or if you want a follow-up webinar that kind of demonstrates, setting some of this test up and walking through some of these test cases, let us know if that's useful. or if you have any other topic that we might have missed and that would be helpful for your project, then I think we can set something up in a future webinar for that. Okay, so although we've used ROS for simplicity of this particular evaluation, but Kudan's Lidar SLAM solution also comes in a cross-platform C++ library. So if you have a customized system, you can use that library to actually integrate SLAM into your solution. But let us know. We can help you set up basically an evaluation for non-ROS systems as well. So with that, I guess that's it. Let's open it up to some Q&A.
Awesome, that sounds good. Thank you, Juan. Thank you, Krishtof, for the great walkthrough and explanation. We do have a few questions coming in from the audience, and just a reminder, if anyone has questions, feel free to drop it in the chat. So Krishtof, this is a question for you. When you're doing the live walkthrough, are we using something like LiDAR odometry and mapping to build out the map? And were we using more data sources, beyond LiDAR for that demonstration?
No, so this demonstration was using purely just the LiDAR itself. And actually, I'll turn this over to Juan to answer a little bit more about what's actually happening in the background in terms of the odometry and mapping.
Hi, this is Yoshiki from Kudan. I'm going to answer this question.
Cool.
Yeah. So basically, we doing the LiDAR SLAM, which means like we subsample the Ouster the LiDAR point and make one and try to extract the keyframe. Then and also do the frame-to-frame matching during the SLAM process. So it's kind of like SLAM means like a simultaneous map making and the localization. So it's kind of like making the map, which means I create a keyframe and also doing the tracking on the real time. So it's not, it's SLAM solution. Please add some additional comment.
Right. So yeah, we're only using in this case the LiDAR data. There's no other sensor like an IMU or anything like that.
No, and that's actually a good segue actually. So we have the ability to fuse additional sensor such as IMU, wheel odometry, GPS, GNSS if available. And I think that helps to create a more accurate result or trajectory as well. So depending on the use case, we're pretty flexible in that system. For the evaluation purposes, we don't do any fusing of these sensors just because it adds a little bit more complexity. I think you can get a lot out of seeing how well it works just with a LiDAR. And if you need to bring that up a notch, then we can look at additional sensors that we can pull in.
Awesome. Here we have another question. What is an acceptable frequency for running the LiDAR sensor and the SLAM if we take into account autonomous vehicle speed?
Yeah, so I think for autonomous vehicle speed, we'd recommend 20 Hertz mode. And then you can choose the horizontal resolution mode that best suits you in terms of data consumption. And then Juan, if you want to add anything to that, more than welcome to.
No, I think that's right. So typically, if you're looking at driving speed, highway speeds, you'd probably want to increase the rotation speed as much as possible. So 20 Hertz would work well on a highway kind of condition. If you have slow moving vehicles and you don't exceed, for example, if you're doing a lot of last mile delivery, even 10 Hertz may work with an increased resolution. But I think that's something that you can experiment with as well. And I guess with evaluation, you can take a look at how well the different frequencies actually work for you. Yeah, it's more of an art than a science yet. So there's a lot of tweaking and experimenting. That's where the evaluation kind of comes into play.
Yeah, definitely. So this question goes back to, you mentioned that Kudan, you can fuse with other sensors. can you fuse with multiple Ouster LiDAR sensors?
So that's something that's actually on our roadmap, supporting multiple LiDAR input. So at this point, we can only support one LiDAR. We can have two separate LiDAR systems running, but nothing yet that actually takes in concurrently two LiDAR streams. It's a little bit of a data bandwidth challenge at this point, but we're trying to work through, trying to see how we can actually optimize some of that.
Okay, awesome. I'm sure everyone will be excited when that comes live. I think we have time for a couple more questions here. Does Kudan's LiDAR SLAM perform loop closure?
Yes, so we do actually perform loop closure, and that is a setting in the YAML file. There is a flag that says, I think it's perform loop closure or something. And there are certain thresholds that you can set where it tries to attempt loop closure. One caveat on the loop closure is if you set the threshold too low and you actually do loop close on a particular location and it's not quite right, you can't go back. So we typically we typically record, I guess, our ROS bag, and then we try to tweak the settings to see what is the right threshold to actually perform loop closure on, because we can't recover to the previous map once loop closure happens. So that's something that you just have to be cautious about. But yes, we do perform loop closure.
Awesome. Another question here is about, is it possible to generate a map that's colored by using the intensities of the reflectivity values?
Yes, so that is an option that we have. It's not actually included in this evaluation version, but we do actually provide intensity, I guess, intensity infused point clouds as well.
Cool. And I think we have one more. We can probably take one more question here. A lot of sensor fusing questions. Can we fuse with IMU and GNSS?
Yes. Yeah, you can fuse with IMU and GNSS. Just with this evaluation version, you don't have that ability, just because there's a lot of variations in terms of the data format and all that. So it's very difficult to have one single mechanism to actually handle that. So one thing we do have is, once you feel like LiDAR only SLAM is a possibility for you, then you can reach out back to us, and we can run your data through our full system if you provide the raw data stream for both the LiDAR, the IMU, and the GNSS. And yeah, and you can take a look at that.
Cool. Unfortunately, that's all the time we have, but thank you so much, Juan, Krishtof, Yoshi, for joining us today. And thank you everyone who stuck around for the great questions. As Paul mentioned, if you have any other questions, feel free to email us at lidar@ouster.io or Kudan at contact@kudan.eu. And this webinar will be on demand within 1 to 2 days. And so feel free to come back and refer to the walkthrough or anything we talked about today. And with
Thanks,
that,
everybody.
thank you, everyone.
Thank you, everyone.
Bye.
Bye.